expertise and that no one person has. And so we all, one of the things that's I feel very proud of our students about is that we spend the semester spending a lot of time outside of our own disciplinary comfort zones, and it's something that we all have to get used to. And likewise, the other thing is I feel like it draws tons of expertise from our students that are not their current primary field. People who have undergraduate degrees in chemistry are now in environmental sciences or in engineering, and so it really draws on all of them also. I want to acknowledge not just my co-instructors, but the other people in the room and outside the room who have supported the students. Amanda Cattermole has supported the students. Claudia Polsky came in and gave a guest lecture. David Faulkner, who provided some teaching and guidance about predictive toxicology, computational toxicology, and our former students in the room. And we've also received past funding from US EPA, and John Katz is here to see your presentations also. So with that, I will just, I'll turn it over to Tom to introduce the SLA group, and we'll get started.
Okay, well, thank you, Meg. And I would really like to thank Meg and Billy Hart Cooper, who did the lion's share of the teaching for this class. They really have done a great job, again. Also, I wanted to thank the people who have helped this particular team, Justin Boers, who couldn't be here today, but maybe is zooming in, and Nicole Panditi, our researcher at BCGC, giving her expertise in 3D printing. Justin advised about chemistry, so we're very appreciative of that, and also to the US EPA for funding our P2 project, which this is supporting. So today this is one of two really great stories about finding a replacement for something that works really well, except for one little itty-bitty problem, right? That it's not so great for human health or the environment. In this case, acrylate-based cross-linkers for SLA resins. So without further ado, and also I want to remind you guys that we'd like to take pictures at the end with our sponsor if we can, but without further ado, I'll let the SLA team proceed.
So like Tom said, we're going to be talking about safer resins for stereolithography printing. I'm Jacob. I'm a second-year MPH student in the Industrial Hygiene program.
I'm Rachel. I'm a fifth-year PhD student in environmental engineering.
I'm Lauren. I'm a fourth-year undergraduate chemistry major.
I'm Kyle. I'm a second-year MPH student in EHS with a focus on industrial hygiene.
Hi, I'm Leanne. I'm also a second-year MPH student in industrial hygiene.
So stereolithography is a type of 3D printing or additive manufacturing, and it's part of a rapidly growing industry. And an article in the International Journal of Academic Medicine from 2018 estimated stereolithography to be around a $700 million industry, and they expect that to grow to $9 billion in the next few years. So stereolithography, or SLA, works by UV photopolymerization, and it's able to make these really highly customizable and intricate objects like those seen here. It's great for biomedical applications like hearing aids, and in fact industry experts estimate that there are 10 million 3D printed hearing aids in circulation, and that over half of the hearing aids that go to market are 3D printed. And it's also great for producing low overhead prototypes, so things like this Aston Martin headlight. And it's great for producing things with geometric flexibility. So how does SLA work? Well, there's a vat of resin, and there's a laser beam, and this build platform. And the way it works is the UV light shines at the top of the layer of resin, and layer by layer, this build platform moves down and produces this 3D object by photopolymerization. So the resin is predominantly composed of acrylates, and these reactive oligomers and reactive monomer. Over 99% of the formula is composed of this. There's also a photoinitiator and UV blocker, but for the purposes of our project, we really focused, our scope is really on these reactive monomers and the reactive oligomers and the reactive monomer, these acrylates. A previous Greener Solutions team looked more in depth at the photoinitiator and UV blocker, and we we refer to some of their findings in this report, but it's not our main focus. So methacrylates are really, really good at their job. They're efficient and fast at polymerization. They are easily functionalized for tunable viscosity and mechanical properties. And they produce polymers with low volume shrinking to provide reliable structures. But the same reasons that they're such good workers also are the reasons that they're inherently toxic. And so I'm going to go into some of the toxicity on this slide. So this is really what we're trying to address with this project is these hazards. So there's a number of issues related to human toxicity with these acrylites. They're irritating to skin, eyes, and the respiratory system. They can cause severe allergic reactions. They've been shown to induce chromosomal aberrations, and there's large data gaps on carcinogenicity and reproductive and developmental toxicity. They also have a negative environmental impact in terms of their lack of biodegradability and potential for bioaccumulation and also toxicity to aquatic life. And once an object is 3D printed, 20 to 30% of the unreacted acrylates remain in the final print, and this poses a hazard to the printer and the user. And in addition, this has to be washed. These acrylates have to be washed off in a isopropyl alcohol bath, which generates hazardous waste. So that's another issue. So with those issues in mind, we created some key attributes that we'd like to see in any of our alternative solutions. We wanted something that was non-irritating. We wanted something that wouldn't cause allergic reactions, that's not expected to be carcinogenic or reproductive or developmental toxicant. And we didn't want that 20 to 30% unreacted material in the final print. We also wanted to promote healthy ecosystems through finding solutions that are biodegradable, that don't bioaccumulate, that aren't toxic to aquatic life, and that generate minimal hazardous waste. And we also looked a bit at sustainability and where our chemicals come from. Do they come from fossil fuels or renewable feedstocks? And so with all of those attributes, we created specific target goals that we wanted to see, and I won't go through each of these, but I'll give some examples. So the acrylites, one of the major problems was that they're irritants, and so we wanted to find chemicals that had negative results from animal testing or in vitro studies. And for bioaccumulation, for example, we wanted to find chemicals that had a log optimal water partition coefficient of less than 3, which indicates that it's not likely to be stored in animal fats and bioaccumulate. So with all of those targets, we evaluated each of our solutions using a standardized approach. First, we looked at authoritative lists like IARC, the International Agency for Research on Cancer, and California's Prop 65, which has lists for developmental and reproductive toxicants and carcinogens. And then we moved on to literature reviews and looked at peer-reviewed papers for additional toxicity data, and ToxNet, which compiles peer-reviewed toxicity data. And then we filled in remaining data gaps with manufacturer safety data sheets, which include the GHS Globally Harmonized System classification data for a number of endpoints. And then finally, we attempted to use predictive toxicology software, but this was largely unhelpful for the types of molecules that we were looking at.
So moving away from the health and environmental performance, we also needed to come up with solutions that could perform technically for this application. So existing SLA resins, they have certain kind of industry standard or characteristics that allow this actual SLA printing mechanism to take place. So you have to have a liquid formula that when you introduce light, you can accurately and reliably kind of end up with a solid printed object. And so kind of looking at these characteristics and then also the strength of the final print that you arrive at, those are some technical performance areas that we really needed to look at. So what we found is we quickly found alternatives, but many of the kind of these metrics that I was discussing, and I'll go into further, had significant data gaps, or what we found in the literature were very novel methods, looking at this question or similar questions that only really arrived at a proof of concept, but didn't have a real fleshed out example. So we really had to come up with a framework of how we could take meaningful information out of these things, evaluate them, and also kind of, given we can't know everything, what are the most important questions we want to ask? What are the most important technical criteria we kind of want to establish to assess the legitimacy of an alternative? So what we decided is fundamentally we thought about, what are the real contexts and uses of SLA technology? And what we found is that SLA is primarily being used in hobbyist settings, in research settings, and biomedical applications. And so what that meant is, when possible, we wanted to go with certain industry standard technical criteria looking at what I was discussing. But if this was not possible, we wanted to focus on things like the speed at which an alternative could print, the precision that it could do it, because this is connected to kind of the hobbyist or research settings where you're making intricate models. And we also decided that maybe we could sacrifice strength to a certain degree, because SLA prints usually aren't being used in functional parts. There's other 3D printing technologies where, for example, you can print metal parts that can actually be used in mechanical equipment. So that was the kind of rough framework we established. And that translated to some specific actual technical criteria. So in terms of speed, which I was discussing, we wanted to find a target or a solution where a material layer could cure in under 10 seconds. So as Jacob was talking about, you have the different layers of the print being irradiated by the light, and every 10 seconds you're capable of printing a cross-sectional layer. So that's very important. And that's kind of the industry standard that you see. The viscosity of the liquid formula that you have is super important, and a kind of constraint and governing factor that determines how accurate and the layer thickness that you print out, because you want to be able to quickly print the top layer and then have the fluid kind of flow away and be somewhat viscous and not be sitting there. So it creates unnecessarily thick or inaccurate prints. There's also a metric called dimensional accuracy. So when you print these things, you're developing what are called CAD files in a computer where you're drawing up a design. And a dimensional accuracy is essentially saying, what dimension, let's say it's a small circle or the corner of a little print, the dimension of that I put in the CAD file, we want the actual thing that prints out to be within plus or minus 0.1 millimeters of what I intended it. So essentially, am I printing out what I intended to, which is obviously very important. And then we decided to look at strength, as I was talking about. So the strength and the thing that was kind of difficult about developing this criteria is that depending on the application you're using, there's a whole field of material sciences that are getting into complicated metrics of a kind of strength or technical performance of a part. But we decided to kind of narrow the focus to just either if a method demonstrated a metric of a certain amount of tensile strength, compressive strength, or its modulus, which I'll explain what that is later in the presentation. If that was demonstrated to be at the megapascal order of magnitude, we decided that would be a legitimate solution. And that was based on input we had from Nicole about what the kind of industry standard strength is of parts. So that was our rough industry standard criteria and framework for technical performance.
So taking all of these different criteria and concepts in mind, we came up with a suite of different strategies to pursue to look at alternatives for SLA printing. And these 5 strategies that we're going to talk to you about today represent a gradient as far as their place in technology development. So we'll start with a strategy that we call functionalized biopolymers, where we have a lot of evidence about how this strategy performs with respect to the criteria that Jacob and Kyle laid out. And we'll move into some different strategies that maybe less is known, but we think they're promising. And as we get to the end, you'll see that we think that we have some ideas that may be disruptive, that maybe are not yet fully proven, because as we know, if there was a strategy out there that worked, that everyone knew worked, we would probably be using it. So with that, we're going to move into our first strategy, which we call functionalized biopolymers. In this strategy, we're using polymers that are found naturally particularly in organisms, and we were inspired here by nature's ability to create different material properties with the same basic building blocks. So here I'm showing 3 different parts of organisms, from the soft sort of shell of the body of a caterpillar to a hard fish scale, and all of these are composed of a combination of chitin and proteins. So chitin alone is fairly soft, it's fairly malleable, and that's what a caterpillar shell is, almost entirely chitin. And as you move to these harder structures, they have a higher and higher content of protein. So we took this concept of what if we took a simple building block of a single biopolymer and we're able to use that as the functional material in SLA printing. Another reason this was exciting to us is because these materials actually in some cases are available as a waste product of an existing industry. So for instance, chitin is producing tons and tons of it per year as a waste product in the seafood industry, and is currently used already after being functionalized to a related material kind of sand. So we looked at both chitin and proteins, and we're going to talk in more detail about using proteins in SLA printing.
So one example of this is bovine serum albumin, which is a protein derived from cows, and the application of BSA to SLA printing was actually published in a paper by the University of Washington. And so the motivation to use BSA kind of came from this desire to have a biosource and biodegradable polymers in SLA printing, which doesn't really exist right now. And so, and it was also another motivation for it was to use in hydrogels for a very high load-bearing application. So a desire to have like better mechanical properties in hydrogels. And so they chose BSA because, as said before, in order to get the fine resolution, you need a very like low viscosity so that the resin can flow in and create that layer. And so the thing about BSA is that it has a negatively charged surface, and it causes like low aggregation. So because the proteins repulse each other, they don't aggregate together, which will affect its printing qualities. And so what the University of Washington proposed is to take BSA and functionalize it with methacrylate moieties, and so this final product can be used in SLA printing, and it was actually demonstrated using a commercial SLA printer. And just to reiterate, BSA is going to have a market worth of predicted $304 million by 2025, and this is really exciting for this application because it means that BSA might be more commercially available and a little bit cheaper to actually apply commercially. And so how this is done is, so like I said before, the use of this resin has been proven to work using a commercial SLA printer. And after you SLA print, there is an additional step they call post-print cure. And basically what they do is they do a thermal cure and they heat up the final printed construct, and this denatures the protein. So the final product not only has physical crosslinks caused by the acrylates cross-linking, but it also has these intermolecular interactions between the denatured proteins that helps improve its mechanical properties and makes it comparable to industry standard.
So looking at the technical performance of how this solution works, we actually found that in these 3 of these metrics that we set out at the beginning, this method actually demonstrated being within the range of what an industry standard resin would actually, how it would perform in terms of viscosity, curing speed, and dimensional accuracy. And one thing that this group out of the University of Washington demonstrated was the dimensional accuracy. So basically, what they did is this is their CAD file that they intended to create with these with known perimeters of these rectangles and squares. This print is from an industry standard print, and then this was using the bovine method. And what they were able to demonstrate was that the bovine method could reproduce these exact dimensions at a rate that was excellent, plus or minus 0.07 millimeters. So this kind of proof of concept demonstrated the high accuracy of this method, which was quite impressive. Moving into the mechanical strength, to kind of give you folks an overview, because I'll be referencing this metric going forward. This, in classical materials testing, this is what's called a stress versus strain curve. So this y-axis is representing the amount of force per unit area that you're applying on a part, And strain is a ratio of how much the part is actually stretching and how much it's straining with respect to its original length. So it's a measure of essentially how much force you can apply to a part before you start seeing it deform. And what's really meaningful is this light blue region, because what this represents and what this point essentially represents is the amount of stress you can apply to a part before it's going to permanently deform. So that means if you have a print, it's able to withstand that much force and not lose any of its structural integrity. And what this group was able to represent, or was able to find, was that the BSA parts could actually withstand a load of 10 megapascals without permanently deforming, and that is, again, within the industry standard criteria of the megapascal order of magnitude that we were looking for. And so just keep that in mind because I'll be referencing that. And then the last measurement that's really important is there's another mechanical strength property called the modulus, which gets reported, which is actually the slope of this region before you start to see permanent deformation, and that's called the modulus value. So that represents essentially the stiffness of a part. So in other methods, I report a modulus, so just so you're oriented to what that kind of means, it's a proxy of a material's stiffness. So looking, so the graph I showed before was a tensile test where you're pulling a part on a part. They also reported compressive strengths, is where you're pushing a force and trying to compress a part. And what was interesting about this method too is that the parts that they printed were actually able to, depending on engaging in that post-curing step or not, you could actually have different kind of applications and manifestations of how this would print depending on the level of water that still existed in the print and water that absorbed. So this print could exist in a kind of swollen hydrogel format where it's taking on and absorbing a certain amount of water, or the cured and dehydrated print that Lauren was talking about, where you kind of engage in this thermal processing step at the end. And what this group was able to demonstrate was a 4.27 megapascal compressive strength in the kind of swollen state, and a 97 megapascal compressive strength before the part strained by 20%. And this is a kind of visual of the swollen state where it has a little bit more water absorbed and then the decured. And you can also, I like this image because you can see the kind of really accurate fine nature of the print and the scale where you're getting this really accurate, elaborate print at the size of about half of a quarter. So again, encouraging results technically where we're seeing adequate levels of strength that you would see in an industry printed part. The last thing that was very interesting about this method is that there's an element of kind of tunability, or ways that you can move around the formula, particularly the amount of comonomer that you're having in the print that can result in different mechanical properties. So it's important to, I think, stress in the beginning of this project, our goal was to actually completely take acrylates out of the equation and figure out ways to cross-link without using acrylates. What we found is, and what was kind of discussed, is that's very difficult because the same reason is why they're so effective is why they're so toxic. So what this group did is actually just reduce the quantity of acrylates that they're using and tack it on to more sustainable biopolymers that, for example, will exhibit a lot better properties, like in terms of being disposed in the environment. They're not going to be as persistent. So this was what was cool is essentially what this column is describing is the level in terms of weight percent of the co-monomer of acrylate that they were using, and then how that manifested itself in different mechanical properties, and whether that thermal cure step was used. So another promising aspect of this formula is you can actually kind of tune your formula to be less toxic, contain less amounts of this comonomer, and still arrive at acceptable levels of mechanical strength that would compare with what we see in the industry, but you have the plus of it being less toxic. So that was the kind of big picture, another huge thing that we found with this strategy. So to close this one out, BSA, like I mentioned, in terms of all the main criteria we were looking at, it was meeting industry standard, and we feel it actually could potentially be an avenue where there's a value add compared to what exists on the market. And the kind of area that could be exploited with this kind of tunability of properties I was just talking about. And then this demonstration of having these kind of hydrogel prints that have a certain amount of water absorbed and dehydrated prints that could be used for different applications. Hydrogels, for example, are really, we found in the literature, used in a lot of drug delivery or kind of novel biomedical contexts. So this is another value add of this solution, is the difference in the kind of applications that could really be used at. And so that is something that could be taken and run with and maybe exploited in the marketplace.
So to summarize the health and environmental performance of this strategy, compared to PR48, BSA has much larger building blocks which make it less bioavailable, and this means that it's less likely to penetrate skin and that it's less volatile, so the inhalation exposure is decreased. BSA is also virtually non-toxic and not expected to be a dermal sensitizer, and the user who is actually handling the final prints is not exposed to any toxic acrylates anymore. However, an ongoing concern with this strategy is that the workers that will actually be functionalizing BSA with methacrylic acid may be exposed at that stage.
All right, so moving on to our second strategy, which we're calling photo-initiated click chemistry. And in this strategy, we explore materials present in plants, particularly in hard plant structures. But before I jump into that, I'm going to give you a little primer on what I mean by click chemistry. So click chemistry is the use of specific functional groups or moieties or modular units that selectively react with each other at high yield and one-to-one reactions. So the field of click chemistry, which has been around for a couple of decades now, was actually inspired by natural protein synthesis, where we see these small modular building blocks being linked together into long chains. But unlike in natural protein synthesis, where we need an enzyme to control this process, in click chemistry, we have specific functional groups that directly react with each other with no enzyme or intermediary. And so in this process, we're actually proposing using functional groups that don't require a photoinitiator, that directly absorb light and then undergo a one-to-one chemical reaction. This strategy has been used before with a PEG backbone, so a polyethylene glycol backbone, functionalized with a maleic acid and a benzophenone group. And these undergo a photoinitiated reaction that then forms a cross-linked structure. But in our strategy, we didn't want to use polyethylene glycol as a backbone. Instead, we wanted to use lignin. Lignin is a very prevalent biomonomer present in all cell walls. It provides structure to plant cells and is also present as a waste product of existing biomass and ethanol industries. So lignin is a polyphenol. It's also easy to functionalize with different functional groups. So we propose using lignin as our backbone for this printing strategy. We have evidence, we know from previous work that lignin can be functionalized with maleic acid groups, which undergo photoinitiated reactions with furan groups to form cross-linked polymer structures. And so in this strategy, we propose in the upstream formulation stage, functionalizing lignin with both maleic acid and furan functional groups, which will then undergo a photoinitiated reaction in the resin to form a cross-linked structure. And in this strategy, so as I said, this technique has been demonstrated with a PEG backbone. It's also been demonstrated that lignin will undergo these same reactions when functionalized with maleic acid and using a thiol-based furan cross-linker. So we're going to talk about the results, the technical performance of those studies.
Very good. So moving into the technical performance, the first bit of information relating to the speed that this process took place was that the polymerization was slow, taking place on the scale of hours. But the caveat I want to add to that is, unfortunately, this group did not report the amount of material that they were polymerizing. So the fact that it took hours when you don't actually know the amount that's kind of a meaningless. What we're trying to get at is a rate. But I think this is this kind of illustrates issues we ran into in the literature where people that are kind of engaging in these things are not thinking about how do we come up with a better SLA and thinking about reporting metrics that are meaningful in that regard. So this is something that would need to be optimized for kind of faster cure speeds or look further into the literature or attempt to kind of demonstrate to see if this could be printed in a layer by layer context. And then in terms of strength, what this group was able to report is they actually engaged in tensile testing. These are what are called dog bone samples. So in material testing, these are standard parts that you basically construct out of a material, and then you engage in a test where you pull it apart until it fails. And this is standardized all across the world, the dimensions of these dog bone samples. So anyone that's doing mechanical testing anywhere, it's to generalize kind of results and make it meaningful. So what we saw is that depending on the linker functionality and getting into what Meg was talking about cross-discipline, that's something I don't really understand at all, but luckily Rachel and Lauren deeply understand that. So what they were able to kind of explain to me is depending on the moieties, that at 4 we were able to see a yield strength level of in the range between 3 and 4 megapascals, which again is hitting that criteria of strength appearing at the megapascal order of magnitude. So a couple of question marks around the speed at which this reaction can take place, but the strength, once you arrive at it, is promising.
So for the health and environmental performance for lignin, it's kind of similar to BSA. Lignin has, the functionalized lignin has larger building blocks, which make it less bioavailable. And lignin is also virtually non-toxic and not expected to be a dermal sensitizer. And a great thing about this strategy is that it eliminates the use of a photoinitiator, which, if you remember from our intro slides, was the 0.5% of PR48 that was very hazardous. However, another ongoing concern is that we are potentially moving the hazard upstream with workers who are functionalizing lignin with maleic acid and benzophenone. Maleic acid is a skin irritant, but just for context, some toxicology studies have shown that a 20% aqueous solution of maleic acid in water produced only mild and reversible skin irritation. However, benzophenone is a possible human carcinogen. It's classified as an IR group 2B, and it is a suspected endpoint.
Okay, so moving on to strategy 3. Strategy 3 we call pH-induced photopolymerization. And in this process, we were taking inspiration from the strong threads of muscle visceral threads that attach muscles to wet rocks as the tide comes in and out. So these threads are actually formed by the muscle when it induces a localized pH change that allows its biomolecules to form strong, hard, and firm structures, even in a wet and highly changing environment. So by inducing a localized pH change, we can go from a liquid to a solid state. In this strategy, we propose using ribose cross-linked collagen. You may be familiar with collagen as a very common protein in bones and ligaments and other biological structures. Collagen itself is a fairly brittle material alone, and it's much stronger when cross-linked with a reducing sugar like ribose, as well as when it's in the presence of a mineral phase mixed with the organic. So mineral phase like hydroxyapatite. So think of your bones, they're a combination of calcium phosphate, collagen, and these materials have been used in other 3D printing contexts. And in particular, they're used, for instance, as scaffolds for bone scaffolding, for bone regeneration. So we have evidence of the printing efficacy of these in other printing contexts, though not so much for SLA. But here we know that here we're interested in the use of a pH change to induce the formation of these structures. So our proposal here is using a resin that's comprised of collagen, a reducing sugar, ribose, calcium, and phosphate. And inducing a localized pH change, we expect to form, as the pH increases or becomes more basic, a composite structure that is very hard and very strong. We will induce this pH change using what's called a photo-base generator. So a photo-base generator is a molecule that absorbs light and releases a basic moiety, something that increases the pH in that specific location, in that region of what's been irradiated. And the previous Greener Solutions team that worked on 3D printing technologies in 2015 looked some into photo-base generators, and so we've taken some of what they reported about the most efficacious and also safest photo-based generators, and proposed using those in combination with these resin materials to form a collagen-based structure.
Very good. So moving into the technical performance, I think kind of what Rachel was getting at is an advantage that we saw with this alternative is that it was actually a proof of concept was demonstrated that this material can be printed. The caveat is the printing technique that was used was what's called an extrusion, and that's where a material is actually coming out of kind of a fine tip and slowly building, as opposed to SLA where you're pulling something out of a liquid vat. But this idea that this material could actually be printed in a reliable and precise way was very encouraging. What this group reported was that it was actually able to print layer thicknesses of the material at the micrometer scale. And you may be saying, well, why is there millimeters on the board when I'm talking about micrometers? And the difference is this is demonstrating the kind of dimensions of the end thing that they printed, so that, for example, the diameter of the circle in the middle is 4.8 millimeters. But the actual progressive kind of layers that it printed at, each cross-section is only about a micrometer thick. And that's really important because the thickness of the layer that you are able to print at is really going to govern how precise your prints can be. So in a way, a layer thickness this low, we kind of roughly assume to be a proxy for high dimensional accuracy, and we'll get into that later. But again, that dimensional accuracy wasn't reported, unfortunately. And then the disadvantage is we saw lower strength metrics in this solution. So we saw strength metrics only reported in the kilopascal range, which is about 1,000 times below the industry and our criteria. But another caveat we wanted to add to that, and we'll discuss at the end, is that we found evidence in the literature that slightly adjusting the formulation of this print, depending on the kind of contents which Rachel and Lauren can get into, actually is hypothesized and I believe demonstrated to actually improve the strength slightly. So that was the summary of this strategy's technical performance that we found.
So for the health and environmental performance, ribose and collagen are virtually non-toxic and not expected to be dermal sensitizers. And as Rachel mentioned, hydroxyapatite is an inorganic material made of calcium and phosphate that makes up our bones and teeth, so it's also expected to be non-toxic. However, the photo-based generators can exhibit skin and eye irritation, acute mammalian toxicity, and ecotoxicity. This was the focus of the 2015 Greener Solutions class, so we kind of summarized the results and chose the least hazardous ones, and we decided that tertiary ammonium salts may be the best photo-based generator for this strategy because of its water solubility and high efficiency and high yield. So now going into our next strategy, which is on unmodified natural protein cross-linkings via photocatalysts. And so this came from an inspiration from seeing some structures found in nature, such as spider webs and squid beak, which are made out of biopolymers that are like blended with proteins. And so the way that proteins can be like modified or synthesized so that they have a structure that will support these kinds of different structures was really the basis for this application. And so this actually came first from this analytical technique called photo-induced cross-linking of unmodified proteins called pickup. And like I said before, it's an analytical technique, so it actually wasn't originally meant to be used for mechanical structures, but rather used for observing architectures and interactions of proteins. But it has known to be have very high yields of cross-linked products and can be obtained with irradiation times of less than 1 second. And I have a little mechanism written up here, but basically how it works is the protein, upon exposure to, with a ruthenium catalyst, upon exposure to light, it causes cross-linking between tyrosines in the protein, and it forms a physical covalent bond between those. And so, like I said before, it was an analytical technique, but a paper out of the university, or Utah State University,
actually tried to optimize this analytical technique and try to make like hydrogels that with mechanical strength that can be used in applications for in the biomedical industry. And so basically what they did is they took recombinant spider silk proteins, they added the ruthenium catalyst and ammonium persulfate as the electron acceptor, and they irradiated it with light, and that caused these physical crosslinks. And they actually produced their own crosslink initiating photodiode or clip, and they made their own light source for this, and it's an 18,000 lumen 465 nanometer LED. And they use this. And how they did it though, just another caveat I'll add, is they did not use this in an SLA context, so they actually just took a mold filled with the resin, and then they just bombarded it with a bunch of light, and that's how they formed their structures. And they did this, the irradiation time was around 4 minutes, so a little bit over our industry standard, but I will say they did it to a whole mold of like a mold of the resin, as opposed to like a layer by layer structure, which would be used in an SLA context. So we think that it might be promising, and if like we applied this system to the SLA, we could probably get promising results from that. And so another added value that we have with this specific application is this post-modification. So what this paper said is that you could take these cross-linked hydrogel products, and if you put them in a bath of different solvents for, I think they only put them in for a minute, and what happens is it causes these drastic changes in the physical properties and by extension the mechanical properties. And so depending on what kind of application you want, what kind of texture you want, you could change, or you can put it in some sort of post-modification that will change its properties.
Moving into the mechanical properties, I think the biggest highlight with this strategy, kind of reproducing the spider silk mechanism, is this was actually the strongest strategy that we found in terms of the reported strength values. So we see a maximum stress of actually over 13 megapascals, and then also a Young's modulus value over 100. So out of all the strategies, this represented the most potential in terms of strength. And then, as Lauren was talking about, there's a couple of questions remaining about the speed at which the reaction could take place. As she was saying, there was kind of a small vat of the resin that they irradiated, and it demonstrated taking 4 minutes. But again, you run into that same issue of what does that actually mean when we care about thinner layers and thus less quantity of material that we need to irradiate in a short amount of time. But also the thing that was interesting about that paper is they found metrics that were actually reporting kind of the speed at which some of the cross-linking mechanisms that they cared about were to take place, and that, I believe, was only being demonstrated on the order of seconds, so it's very promising in those regards.
So this spider silk strategy presents a number of benefits. The resin, which is made up of ruthenium and ammonium persulfate catalysts and those recombinant spider silk proteins, is a water-based formula. And also these recombinant spider silk proteins in the study that Lauren mentioned earlier were found to be non-cytotoxic, and they were presumed safe for biomedical applications. But there are some problems, especially with those catalysts. Ruthenium is one of the rarest metals on Earth and can only be mined in certain areas of the world like South America and South Africa, and so that really presents some problems for, especially for sustainability. And also the hazard information about ruthenium is really sparse. There wasn't very much data. But fortunately, in the formula, ruthenium only takes up 31.35 micromolar, so that's a very small portion of the formula. Ammonium persulfate, the other catalyst, is a skin irritant and has been shown to initiate asthma and is hazardous to the aquatic environment. And it's really on par with our PR formula in terms of its allergic potential. It's categorized in the highest GHS hazard category for skin and respiratory sensitization, so that's a problem. But again, even though it's 100 times more concentrated than the ruthenium in the formula, it's still a relatively small amount in the overall resin.
And then the last strategy we're going to be talking about is encapsulation techniques, and this is probably the least researched area, but I think that these techniques have really cool applications that can be applied to SLA printing. So this kind of came out of the idea of what if we could like shine light on something, it opens up and releases chemicals, and these chemicals can cross-link, or they can cross-link. And so basically what I envision is you have like a sort of micelle structure or encapsulation structure with cross-linkers inside of it, and upon exposure to UV light, the micelle or the encapsulation opens, releases the chemicals, and these cross-linkers can either cross-link with a biopolymer backbone, like seen in the top figure, or they can cross-link with themselves upon exposure to UV light, like acrylates do, and they could make their own cross-link structure. And ideally, this encapsulation technique can be reversible. So upon exposure to another stimuli, if you see the back and forth arrows right there, upon exposure to another stimuli, it can actually re-encapsulate the chemicals that it once released. And so there are a variety of encapsulation techniques that can control the release of chemicals. It's actually a very well-studied area, or a very prominently studied area, especially in terms of drug delivery. So one of these is, like I said before, micelles, which are a structure that has a polar and non-polar area on its structure, and when it is exposed to a sort of solvent, it will form these little encapsulation, like little bubbles. An example of this is like in soap. The soap bubbles will like encapsulate around the dirt, and that's how it like cleans. And so a lot of micelles, like I said before, have been used in drug delivery, and through controlling chemical and physical properties of the micelles, such as choice of monomer, polymerization degree, and architecture, you can control things like release time, the dosage, like the amount you release at a certain time, area of release, and recapture the chemical, and more. And I think that's why it's really, really exciting, especially since it's used in drug delivery, where the location and the time and the stimulus that you use to release it is very, very important. I think that further research in this area in the context of SLA printing can be very, very useful. Just one small example of a micelle that I found while looking for applications for SLA printing, this spiropyrin-initiated hyperbranch polyglycerol. And as you can see there, inside the micelle, there are some chemicals, and then upon exposure to UV light, what happens is that the spiropyrin, it turns from a hydrophobic state to a hydrophilic state, and this causes the collapse of the micelle and the subsequent release of the chemicals held inside. And then what's really cool though is upon exposure to visible light, again, the reaction is reversible. So the pure spiropyrin goes from the hydrophilic back to the hydrophobic, and has been proven to recapture a portion of the chemicals that it once released. And like I said before, this kind of mechanism is really useful because especially when you're concerned about like the hazard posed by a lot of the cross-linkers that are used in SLA printing, the recapture of these into these little compartments can help reduce exposure for the user and make the process a lot safer. And another thing I was thinking about is this kind of technique can maybe be applied to a bunch of the other strategies that we used before. There has been hazardous components in each of the strategies that we have, but maybe we can mitigate some of these hazards by having specific encapsulation techniques for those specific molecules and reduce the hazard of those.
So one of the great benefits of the micelles is that when you take into account your technical performance when you're designing your micelle system, you can also incorporate your health and environmental performance. So micelles, they offer a high degree of control over the inputs and processes. And also the spiropyrins that Lauren mentioned on the previous slides, those were found to be non-toxic to WI38 and HeLa cell lines, so that's promising. Some ongoing concerns, however, with micelles is that, again, they're really largely dependent on their design and application. And so, again, really health and the environment should be taken into account when designing for SLA. A study on the nanotoxicity of micelles also found that nanotoxicity was correlated with the unique structure of the micelle, but even when looking at one particular micelle, it found that the biosafety was different in different cell models, and that there wasn't any correlation between in vitro and animal tests, which really shows that the toxicity is highly variable and uncertain. So this remains quite a large data gap in terms of health and environmental performance at this stage.
So moving on to kind of concluding and synthesizing our findings, we're going to kind of present the pros and cons of all the strategies that we outlined, and then kind of propose a framework of an opportunity map for industry and academic stakeholders to kind of take our research and run with it. And where, you know, as Lauren was talking about, we have some strategies that are very promising, but you know that would obviously entail more research and R&D and stuff like that. So our goal for this project was to kind of get a sense of the landscape of the alternatives here, and then provide a conclusion and synthesize findings for all 5 strategies. So looking at the technical performance, we wanted to kind of create graphics for not only technical but EHS performance and synthesize. So what we did is we created a kind of rubric where we had a high performance, medium, low performance, or unknown for each of these kind of metrics we discussed. So high performance was kind of if we saw evidence reported in the literature that was meeting the industry standard criteria. Medium was maybe there was some evidence reported that maybe was not quite adequate, but there's also simultaneously evidence that this could be improved upon, or if they were reporting information that wasn't exactly what we cared about, but could kind of reasonably be assumed to be a proxy of information that we cared about. We categorize that under medium. Low performance is not good enough and no real evidence that it could be improved. And then lastly, data gaps, which unfortunately there's quite a few of, but that's kind of the nature of doing this type of research. So looking at the bio-based polymers, that was the bovine serum method. That was able to demonstrate high performance across every metric that we cared about. That is no coincidence because that's the one solution we have that actually has acrylate crosslinkers in it. So going back to the foundational problem of this whole project is the reason why they're so effective is the reason why they're toxic. But the value add we saw with this method is that you're able to kind of tune the amount of those comonomers that are bad, reduce them, and tack them onto biopolymers, which presents benefits in the kind of environmental stage and making them not as persistent in the environment when you dispose of them. Looking at the click chemistry method, we saw medium performance because we saw a printing on the scale of hours, but that information didn't get at how much was being printed, so there's still a chance that that could be worthwhile or worth looking more into. No information on the accuracy, but we saw strength of the megapascal range. The collagen strategy, unknown information about the speed at which it was printed, but given that they reported given that they were reporting a layer thickness of in the micrometers, that could be, we made the assumption that that could be a rough proxy for actual very reliable and accurate dimensional accuracy. But again, it's not a for sure thing. And then the strength, given that, I can never say the word hydroxyapatite. Yeah, given that this strategy could be printed and the formula could contain hydroxyapatite, that was shown to actually increase the strength higher than the kilopascal range, which is the paper we got our strength metric from. So evidence that the strength could be improved. Spider silk, the speed, we put it at 2 because we saw cross-linking take place in the range of minutes. But again, that was done in a vat and not the exact layer-by-layer context we care about. Unknown levels of accuracy, but extremely good strength, as strong as we saw out of any of the strategies. And lastly, micelles are kind of the most novel, disruptive strategy we propose that are really, really interesting and probably the area that would be the coolest to actually see some R&D go into because of the kind of really accurate way you can encapsulate, release, and close off what you care about. So yeah.
Okay, so to summarize the health and environmental performance, we see that all of our strategies do have a distinct benefit compared to PR48. And through our analysis, we did look at a number of different toxicological endpoints. And this was to ensure that we don't, for example, introduce a new hazard by accident. Like if we eliminated the irritation or sensitization category for PR48, but then accidentally introduced a strategy that causes cancer, that would obviously be terrible. And the main takeaway from this is that the carcinogenicity column still does have a lot of data gaps, so before we suggest any strategy to actually be adapted into industry, there needs to be a lot more research into the actual endpoints concerning carcinogenicity.
So looking at that table that Dan just showed, it might be hard to tell where the risk is or what improvement we're actually making. So in this sort of summary table, I'm showing two columns in the formulation and printing and use stage which talk about the health criteria. So as you'll recall in our first couple of strategies, we acknowledged that there would be a lower risk to our user of the printer or our consumer who might receive the 3D printed object because they're using something with a biopolymer backbone. But in the formulation stage, the workers who are actually preparing those resins would still be potentially exposed to hazardous components to functionalize the biopolymers. So whereas in PR48, both the formulation of the resin poses a hazard to workers, and the printing and use of 3D printed objects also poses a risk to consumers. In our first two biopolymer-based strategies, we believe that we've removed much of the risk for the user or the person doing the printing, but that a risk remains for the formulator. In our technical printing and use column, this is sort of a summary of our technical performance criteria, and this is to show that there is a gradient from these strategies that we know how they work and they work quite well, to ones that perhaps still need some optimization, or others that there are quite a few data gaps. And then finally, we separated out the issue of waste disposal. So this is looking at our ecotoxicity and bioaccumulation endpoints to say that some of these still contain some ingredients such as a ruthenium catalyst or a photo-based generator that could be problematic, and we want to keep that in mind as well as we move forward. So based on sort of this level of analysis, we believe that each of these strategies has some reasonable steps forward that we could take, and they exist at different stages, as I said at the beginning, of technology development. So for our methacrylic acid functionalized biopolymers, we think that we're basically at the prototyping stage. Like if someone could take this technology and start trying to print it, start trying to optimize the formulation and considering some of the post-print curing processes or how these different components could be used to create real 3D printed objects. For some of our other alternatives, like the click chemistry, we need to work on modifications to improve the print speed. For our pH-induced strategy, we want to think more about alternative photo-based generators that might not include this ecotoxicity, and do more test printing with hydroxyapatite. The spider silk strategy still needs to be tested in a layer-by-layer printing context, so it hasn't been proven to work in an SLA context. And we also have some other alternatives to consider there. And then the micelles, we would need some fundamental research partners who are going to develop these for us from the get-go to work well in this application. So it's more in a preliminary research stage, but as we said, very promising. And so with that, we hope this gives an overview or a roadmap of where we think we could go from here. And we'd be happy to take some questions. Thank you.
Questions and comments?
Just a quick one about the spider silk. You said that they had come up with their own light source that to generate the photo reaction. And how does that align with what they use for the lasers in current SLA, or can that laser be tuned to that wavelength? And I mean, how do those marry?
Yeah, so the way that they structured it, it's just like a whole array of LED lights, and that's like their light source. So I don't know how it would transfer to SLA. I'm assuming that because they were just bombarding the whole mold with that, that's why they had that huge array, because it wouldn't really make sense to just have one laser beam pointing towards it. I'm not too familiar with the actual transfer into the SLA context, but I feel like if you can tune the wavelength of the light in the SLA printer, then you could probably transfer that to the new resin.
I have a question for you. This was great, thank you, and I love this summary. This is a fabulous way to, you're demonstrating the array of levels of development, so that's as you described it. So a question for your ruthenium catalysts. In current polymerization processes, I think there's some ability to recapture catalysts. Did you see anything in the literature about the possibility of recapturing this rare metal, material, not a metal?
I didn't do any specific research on ruthenium in general. My cells came towards the tail end of our semester where I was just kind of like, that would probably be a cool thing that people can research. But I didn't specifically look too deeply into the specific applications because I felt like there were so many and I don't think I had the technical knowledge to really make a meaningful conclusion from that, but that would be a very interesting.
Oh, so you're thinking about the micelles to recapture the ruthenium, but in your spider cell, for example,
Wait,
in the processing, there's a possibility of recapturing catalysts?
Yeah.
Did that feel like that was something, so not necessarily by a micelle, but in your spider cell processing?
Did I think about recapturing it?
Right.
So
once
in current SLA
Yeah.
printing, there isn't any recapture
fair enough.
mechanism, right? Because you don't have a really valuable ingredient in your resin.
Right.
And so I don't think we've seen an example where people are recapturing any particular component of the resin.
So that would be something if you had a rare catalyst. But
Yeah.
Thank you.
We have a report due for this class in a little bit that kind of synthesizes another thing we could add, because that's something that I don't think any of us thought of, but in like process chemistry, that's always a big thing that I know people are trying to do. So that's a good thought. I appreciate that.
Excellent. I really enjoyed it. I thought the way you laid out the information was really clear, and I want to echo what Anne said. That's such an incredible slide. So thank you, all of you. You did a great job. I have a quick question, and I apologize because I may be incorrect when I say this. I believe on one of your health slides, I think it was spider silk that had a number 3 red concern around, was it a skin irritant? Keep you going back. Yeah. Do you know why spider silk is an irritant? I was really surprised to see that. And did it come as a surprise to you guys?
I don't think it's
It's
not the
not the
recombinant
silk.
spider silk itself.
See if
it's
okay.
this part here. Yeah.
Thank you. I was racking my brain thinking that
Yeah.
doesn't make sense, but thank you for explaining. And really excellent job, all of you. Thank you.
So you mentioned that hobbyists use 3D printing a lot. Which of the proposed mechanisms do you find will be the most economically feasible that will make it affordable to these hobbyists? Because industry has a lot of different financial mechanisms. They have a much wider source, I should say, to economical resources. Which do you think would be most promising for hobbyists?
So as far as like cost,
Yeah, I know you guys don't do cost-benefit analysis with this, but it did come up when I was in the class last year. And we looked at which one would be most economically
So
feasible.
our perhaps advantage in this project is that the resin that's currently used is not particularly cheap either.
Yeah.
And so it's partly interesting to us as that some of our strategies are currently waste products that are pretty inexpensive. So like we talked in detail for the biopolymers about bovine serum albumin, which is a byproduct of the beef industry. But we also looked into that same sort of mechanism for chitosan, which is widely available and inexpensive as well. So some of the base biopolymers are inexpensive, very inexpensive, and are waste products, and lignin as well. But some of the perhaps additives would be where the expense might come in. I would imagine having ruthenium catalyst would not be cheap. But you're right, we didn't do a formal cost analysis. So we just have sort of those general thoughts on it.
I'll just reiterate the comments. It was beautifully laid out. Thank you, very clear. I just came back from a week in Maryland watching presentations where people are still putting up like 100-word slides. You're just like, wow, we're still doing that. So this is the hope, And so I'm wondering if you could put the health and environment one up again. There was your summary slide, and you started to, and maybe I missed it, but I'm wondering if you could just kind of break down where there were sort of upstream worker concerns versus sort of the downstream consumer user questions, and why, so what generated the red? Was it worker or consumer? I just kind of clarify that.
this slide is designating where that exposure happens, so in the formulation versus the printing and use stage. So like for instance, bio-based polymers
Oh,
and
yeah.
chemistry, we rated red for formulation because they have these red sort of ratings in the health categories, but there isn't exposure to the person doing the printing. So we
Right.
put that red under formulation on this slide, but not under printing and use. Does that make sense?
Yeah,
Is it-
yeah, so, okay.
And that's because in many of those cases, it's the acrylates that cause the concern about the PR48 at all those levels, but it's some of those other additives in the bio-based formulas that it's not the basic building block. It's these other things you're adding, but those tend to not show up in the printing formulation, right? Or you're not exposed when you're actually printing. Was that the idea?
Right, so you're not exposed to some of them when you're actually printing. Whereas for like spider silk, there isn't a change in the bioavailability from formulation to printing, so it has the same rating for both. It has it too, which was sort of our overall assessment of the health for spider silk.
And you probably said it, but what is it that the acrylates do in the process?
During the printing,
What's their function?
they are both the backbone and the crosslinker. So they actually are very reactive, so they cross-link with each other, and they undergo a chain polymerization reaction. So they very quickly form polymers from these low molecular weight monomers and oligomers. So there's a photoinitiator that kicks off the chain reaction, and then they react until they're terminated.
Well, one of the reasons I ask is it's under the TRI, toxic inventory reporting. It's by far the most emitted from the Tesla manufacturing plant in Fremont. That's the thing, that's the substance that they're reporting as their largest emission of toxic air contaminants. And so obviously there's some process that they're dealing with there that's using a lot of that.
Contaminant.
It's methyl methacrylate actually that they're
Oh, yeah, that's a salt.
yeah.
The team said this a couple times, and I think it's such an interesting point, is that this is such a hard challenge because the function of the chemical and class of chemicals that you're trying to eliminate and replace, it's a reactive function, right? It's trying to react with molecules to get the polymer that you're trying to produce. And that reactivity is what's responsible for its toxicity. It's what causes its toxicity. And so replacing something reactive with something else reactive is likely to come with a different kind of or a similar kind of toxicity. So it's a real bind, which is why you're looking at this challenge. Like you said, that there isn't some readily available alternative that's obvious. And I think you've worked beautifully in that tension with these sort of subtle ways to try to improve the formulation while still getting the function. But I just want to acknowledge what a difficult tension that is that's in the challenge.
I have a little appreciation statement to you guys. I mean, these guys went from 0 to 60, had no experience virtually in 3D printing at all, and to have to go in 17 weeks across different processes, the actual technical process of printing, and also the different materials and their technical and EHS performance. It's really, you guys have done a great job. And one thing that has come to mind listening to this final presentation is thinking about the components of a system that makes the final product and where your innovation lies. For instance, seeing that you looked at photo-induced reactions as they change either pH or moieties within the chemical reaction, I think maybe that's or polarity, for instance, it's maybe something to think about as you kind of summarize this in your final report. What are we bringing to the world? What is the extra value we're bringing to the world? What is the innovation here? And that's one pattern I see. You don't have to sort of take that and run with it, but it's like, okay, well, let's look at the activator, which is the UV light, and then how did we bring something new to what that activator can do? Or what materials can it work with. So you guys really, you've done really just tremendous job.
Any other questions or comments for our team? I want to just echo and acknowledge that, you know, as instructors in this course, we kind of set the frame and we're the coaches, but the students are doing all the work. We provide some materials and some ask questions and point them in different directions, but just like Tom said, they really start the semester with like a 3-word challenge, and they not only have to solve it, but they first have to really frame it and figure out how they're going to work within that. And it's true of both teams. You're about to see after a break, we'll take a break, and then you'll see the presentation from our team who worked with solvents in manufacturing polyurethane films. In both cases, they really had to come in and understand the system first, understand a complex system that they can get very little information about often, and then start to think creatively beyond what's there. So it's a multi-step process that really takes a tremendous amount of work to cover all of that, and I'm very proud